Dear students, I am Hiba Haq, lecturer of physics from Government Degree Science College, Malir, Cantt. Today I am going to explain the kinetic theory and the ideal gas, which is the topic of intermediate synth textbook. Using kinetic theory, we shall discuss these topics: interpretation of pressure of gas on kinetic theory of gases, kinetic interpretation of temperature, and at the end, verification of gas laws like Boyle's law, Charles' law, and general gas law. So before we proceed, we all need to understand what is kinetic theory of gases. The kinetic theory of gas is a collection of several rules that describes the behavior of gases in terms of interaction of molecules and the energy they have. The macroscopic coordinates like volume, temperature, internal energy and pressure are all taken into account when observing and understanding the gas behaviors. Okay, so let's start. In order to understand the behavior of gas molecules, we need to construct a molecular model of the gases, and for that we make few assumptions. Based on these assumptions, we use Newton's laws to analyze the mechanics of ideal gas, which form the basis of kinetic theory. So these assumptions are: the first assumption is that a gas consists of large number of tiny particles called molecule. At standard temperature and pressure, there are approximately 3 into 10 raised to the power 25 molecules in 1 cubic meter. The second assumption is the molecules are greater distance apart as compared to their dimension. Now next one is the molecules are free to move in all directions with various speed, making elastic collision with one another and with the wall of the vessel in which they are confined. Next one is the molecule exert no force on one another except during collision. In the absence of external force, these molecules move freely in straight line. And the last one is that laws of mechanics are assumed to be applicable on the motion of molecules. Okay, so in this lecture, I will explain the interpretation of pressure on kinetic theory of gases, and in next lecture, we will discuss the interpretation of kinetic theory of gases on temperature and the verification of gas laws. So let's start by considering n number of molecules in a cubical vessel of dimension L. We assume that the walls of this vessel are perfect elastic in nature. So you can see that this is a cube and there are the molecules that are in random motion. Through this GIF, you can easily visualize that these molecules are colliding with each other and with the wall of the vessel in which they are confined. Okay, so if a molecule has a velocity v and it is moving in this direction, then we can draw the component of velocity vector like vx, vy, and vz. So when the molecules are moving in the vessel, so they collide with each other and with the wall of the vessel. So when they collide, they exert pressure. If F be the amount of a force exerted by the molecules of the gas and A be the area, then pressure will be force per unit area, that is F upon A. We mark it as equation 1. So the force that molecules are exerted on each other or on the wall of a cubic vessel is defined as rate of change of linear momentum. So if F be the force and delta P is the change in linear momentum, then force will be equal to delta P upon delta T. We mark it as equation 2. So this delta P, change in linear momentum, is the change in momentum of a molecule due to collision, and delta T is the time required to complete that collision. Now we do calculation. to get the value of force. For that we have to calculate the change in linear momentum of a particle or molecule and the time required to complete that collision. So calculation for the change in linear momentum, we assume that small m be the mass of a molecule moving with velocity negative vx along negative x-axis and suffer elastic collision with the left hand wall. So when the molecule collide with the wall, it bounce back with the same velocity towards the right wall. So for our simplicity, we neglect the molecule interaction. So since the particle is moving along x-axis, then the vertical component of velocity y and z component of velocity remain unchanged. Okay, so linear momentum is defined as the product of two quantities, that is mass and velocity, and it tells us about the quantity of linear motion. So linear momentum of a gas molecule which strikes the wall before collision is minus mvx. We just multiply the mass and the velocity of a molecule, and the linear momentum of a gas molecule after collision will be mvx. So if we want to calculate the change in linear momentum, delta p will be equal to pf minus pi, and mvx minus mvx will be equal to minus plus mvx plus mvx will be equal to 2 mvx. So the change in linear momentum of a one molecule during collision will be 2 mvx. We mark it as equation 3. So after calculating the value of change in linear momentum of a molecule, we try to find the time required to complete one collision. So that for that the total distance covered by the molecule to reach from one phase of a vessel to another phase without colliding with any other molecule will be s is equals to vx dot delta t, where vx is the velocity of a molecule and delta t is the time required time in which a collision occur. So if we rewrite this equation in term of delta t will be equal to s upon vx. This s is the total distance covered during one collision, which is 2l. For example, this is the one phase of a vessel, this is the second phase of a vessel. As we know, the dimension of a cube is l, so when the molecule will move from here to here, it covers a distance of l, and when it bounces back, it again covers the distance l. So this l and the l will be equal to 2l. So equation changes, delta t will be equal to 2l upon vx. We just put the value of s. We mark it as equation 4. Now we already calculate the value of change in linear momentum. We put the value of change in linear momentum and time we in equation 2. Equation 2 was f is equals to delta p upon delta t. So delta p will be equal to 2 mvx and delta t will be 2l upon vx. So this vx will come here, and 2 mvx upon l into vx. This 2 and 2 will cancel, and the final expression of force will be equal to mvx square upon l. We mark it as equation 5. So using the previous expression, we can easily calculate the total force exerted by n number of molecule during collision along x-axis, and this will be equal to fx is equals to fx1 plus fx2 plus fx3 plus up to last molecule, that is n. So this is plus fxn. As we know that fx1 was mvx square upon l, since the mass of all the molecules are same, as we assume that molecules are identical and the dimension of a cube is same. So here just the term that changes is velocity. So the first expression will be mvx1 square upon l, second will be equal to vx2 square, third will be equal to vx3 square, up to last term which is vxn square. And if we sum these all terms, we get the total force. Now we divide this expression by the area of the cubic vessel, which is L square on both sides. So if we divide here, if we get Fx upon L square, and if we divide this term by L square, this will be equal to mvx square upon L into L square plus mvx2 square upon L into L square plus mvx3 square upon L into L square up to last term. So this L into L square is nothing but the volume of a cubic vessel, and if we replace L square by area, so this will the equation changes to Fx upon A is equals to Vx1 square upon L cube plus Vx2 square upon L cube plus Vx3 square upon L cube up to last term. Further, what we do from equation 1, we know that force per unit area is pressure. So this is actually the pressure of the molecules. So pressure will be equal to mvx1 square upon L cube plus mvx2 square upon L cube plus mvx3 square upon L cube plus up to last term mvxn square upon L cube. We mark it as equation number 6. After calculating the total pressure exerted by the molecules during collision with the wall along x-axis, we try to calculate the total pressure. So for that I'm going to introduce a term density. We all know that this is mass per unit volume. We represent it by rho, and since we are talking about a combined effect, so this is the total mass of a molecules divided by volume. The total mass of a molecule will be equal to n into small n. We assume that there are n number of molecules and mass of one molecule is a small m. So the total molecular mass of molecules will be n into small m, and volume of a cubic vessel will be L cube. So we what we do, we find the value of volume from this equation. Volume will be equal to L cube will be equal to n into small m upon rho. We put the value of volume in equation 6. The equation 6 will become pressure will be equal to m divided by n into small m upon rho into bracket vx1 square plus vx2 square plus vx3 square plus up to last term. So this m and this m will cancel. The equation changes to P will be equal to rho Vx1 square plus Vx2 square plus Vx3 square plus up to last term Vxn square divided by total number of molecules, that is n. So this term is nothing but the average of Vx square. So we can write it as P is equals to rho Vx square bar. We mark it as equation 7. Now initially we assume that the molecules are identical. This means that Vx square bar should equal to Vy square bar should equal to Vz square bar. If we talk about the resultant, V square bar should equal to Vx square bar plus Vy square bar plus Vz square bar. So what we do, we replace V square bar and Vz square bar by Vx square bar. Then this Vx square bar plus Vx square bar plus Vx square bar will become 3Vx square bar. So the final expression will be V square bar is equals to 3 Vx square bar. Or we can simply write that Vx square bar is equals to 1 upon 3 rho 1 upon 3 V square bar. So this V square bar is the average square velocity or root mean square velocity. We represent it by VRMS. So what we do, we put the value of Vx square bar in equation 7, and equation 7 will be P will be equal to 1 upon 3 rho V square bar. So from this equation, what we concluded, that the pressure of an ideal gas confined in a cubical vessel depends upon two parameters, that is the density and the average square velocity, and the pressure depends directly upon them. So this is all about today. In next lecture we will discuss the verification of gas laws and the kinetic interpretation of temperature. Hope you will enjoy it. Take care. God bless you.